It is summer and we're going to a lake and we see some lily pads over there and a frog. And the frog is jumping on the lily pads and going to one and then to the other and then to a third one and then back to the first one. And we're looking at the frog and we're thinking, it's actually not quite random how he's jumping. Maybe we can describe his behavior, how he's jumping, with a Markov chain with some states. So we are drawing state 1, state 2, and the state 3, where we see the frog jumping between lily pads, and each state is a lily pad. And we see that frog jumps to the second lily pad with a probability of 0.6, to the third lily pad with a probability of 0.4, back to lily pad 1 from 3 with 0.8, back to lily pad 1 with a probability of 1 from lily pad 2, and straight from lily pad 3 to lily pad 2 with a probability of 0.2. However, it never goes back to lily pad 3 if it is on lily pad 2. With this, we can also create a matrix that denotes all the edges in our nice Markov chain. We have state 1, state 2, state 3, and these are denoting what the weights are between these states. So from state 1 to state 1 there is no weight, so it is 0. From state 1 to state 2 there's a probability of 0.6, and from state 1 to state 3 we have a probability of 0.4. From state 2 to state 1 it's 1, 0, 0, and from state 3 to 1 it's 0.8, 0.2, and 0. There are some properties in Markov chains. For example, every state needs to have outgoing arrows which all add up to 1. If we look at this matrix, each row needs to sum up to 1. And in our case, that's true, so we're lucky. Each node is called a state, and going from one state to another is called a transition. Furthermore, a Markov chain is called memoryless. What does this mean? Memoryless means that even if the frog has done 100 jumps and it is on lily pad 1, the probability that it's going to lily pad 2 is still 0.6. The past does not influence the future. The same thing with memoryless is called time invariant. A Markov chain is time invariant because if a frog jumps is on the first lily pad and jumps to the second one, its probability is 0.6, or it is jumping all around, going to 1 to 2 to 1 to 3 to 1, and then if it's going to node this to the lily pad 2, that probability is still 0.6. The probabilities do not change over time. That's what it means that it is time invariant. So, with these properties, we can ask ourselves a question. What is the probability that the frog is on lily pad 1 given that it was starting on lily pad 1? What does this notation mean of x2 and x0? We're looking at a time. And xt means that the state of the Markov chain at time t, what is happening then. We see that we are talking about state 0, which is our initial state, and we're saying we're starting at state 1. We do not know where the frog is at state at time t is 1. We do, however, know where he should be at t is 2, namely at state 1, and we're looking at the probability of that. Knowing where the frog starts is also called the initial distribution and denoted with pi 0 at the t is 0 time step. In our case, it starts at state 1, state 2 is 0, and state 3 is 0. This also needs to sum to 1. This just shows you what the initial distribution is. Now, we still want to calculate what the probability is that the frog is on lily pad 1 after 2 jumps, when it is on lily pad 1, starting at lily pad 1. And we can do that in 3, you could say 4 ways. The first way is we just write down every combination. We start in state 1. From state 1 we can go to state 2. And now we have to go back to state 1 again, because at time is, this denotes time at t is 0. This denotes the state at t is 1, and this denotes the state of time at t is 2. We want to go back to s, to state 1. Another combination is if we go from 1 to 3 to 1. And these are all combinations that are possible if we start in 1 and go back to 1 2 steps later. We can calculate these probabilities by just looking at the Markov chain or looking at the matrix and seeing what each transition the probability is. So from S1 to S2, that probability was 0.6. Multiplied with the probability of S2 to S1, that probability was 1. So this is 0.6. For this one, from S1 to S3, the probability is 0.4. Multiplied with the probability of going from S3 to S1, which is 0.8. This probability is 0.32. And now we add up these different possibilities, which gives us a probability of 0.92. So, if we start, or if we at one point are on lily pad 1, there is a 0.92 probability that we will end back at lily pad 1 after 2 jumps. This was a very straightforward calculation. However, if your Markov chain gets really big and there are more and more edges, the number of possibilities gets just too much to calculate or to write down even. So we need another method. This method of writing down we call method 1. Now let's look at a different method. We're going to look at method 2. And for this, we're going to use our transition matrix and our initial distribution, because we want to know when the frog starts in state 1. So this is why our initial distribution is 1, 0, 0, denoting state 1, state 2, and state 3, or lily pad 1, lily pad 2, lily pad 3. And our transition matrix was 0, 0.6, 0.4, 1, 0, 0, 0.8, 0.2, and 0. There's something nice about these transition matrices, because if we multiply a matrix with itself, then we actually know the probabilities of taking 2 steps. Right now, this matrix is for 1 step. If I take 1 jump, the frog jumps once. If we multiply it with itself, so we get p squared, our matrix is the following: 0.92, 0.08, 0, 0, 0.6, 0.4, 0.2, 0.48, and 0.32. This is just p multiplied with itself. And what this is saying is, again, from state 1 to another state, so going from state 1 to state 1 in 2 steps, this matrix right now denotes 2 steps or 2 jumps by the frog and its probability. So if we want to calculate with this initial distribution, all we have to do is multiply the initial distribution with this transition matrix of 2 steps. And if you want to have 5 steps, we could just raise the matrix to the power of 5, which results in the next vector of 0.92, 0.08, and 0. If we are starting at the first lily pad, there is a 0.92 probability that we end up on lily pad 1. There's a 0.08 probability that we end up on lily pad 2, and that's a 0 probability that we end up on lily pad, this should actually be 3, on lily pad 3. This is a fairly straightforward method as well. We're just looking at matrix multiplication and our initial distribution. If we want to know if we end up in lily pad 1 again, we look at this value. If we want to know what the probability is if we start at lily pad 1 and we want to end up at lily pad 2, we know the probability is 0.08, and the same for lily pad 3. The downside of this method is that we have to do matrix multiplication, and again, for very large Markov chains and very large matrices, this is very, very inefficient. Luckily, we have more methods to solve this problem. Let's look at the next method. Method 3. Method 3 actually says, well, let's make a table of all transitions. S2, S1, S2, S3. These are our states. And then here we get at t is 0, at t is 1, at t is 2. We're going to create a table denoting probabilities of each state. Well, our initial distribution was that we started in state 1. So at t0 we are in state 1. These are our probabilities then. Now we are going one step further. We're looking at this value. Let's call this value A. How is A calculated? Well, A is calculated by looking at this value. So we look at, let's call this A at t, or in our case, not A at t, it's A at 1. A at 1 is calculated by looking at a 0, so that is this value, multiplied with the transition of going from state 1 to state 1. So we denote that with P11 because we look at our transition matrix. Because we are looking at T0, let's say we also look at 1, so we put a 1 over here. Plus, at time 0 of state 2, multiplied with the probability of going from 2 to 1. Plus A0 from state 3, multiplied with the probability of going from state 3 to 1. In our general case, if we would write down the general formula, is T plus 1 of a state S is the sum of all states S of AT S multiplied with the probability of going from S. Let's call not S, and let's call this I A T not S I. We have to look at all different states multiplied with the probability of going from I to S. This may all look very confusing, but actually what we're saying is going from state 1 to state 1. The probability is 0, so we get 1 times 0 plus 0 times the probability of going from state 2 to state 1. And going from state 2 to state 1 is a probability of 1, as per our Markov chain. Going from state 3 to state 1, we get 0 because this value here is 0 multiplied with 0.8. In our case is 0. So this value of A is not A, but will be 0. The same thing we can do for the next value for S2. So again, going from state 1 to state 2, so we're calculating right now, this was for state 1, we're calculating at time 1 for state 2, we're saying, okay, going from state 1 multiplied with the probability of going from state 1 to state 2, which was 0.6, this is multiplied with 0.6, plus 0 times 0, plus 0 times 0.2, because the transition from state 3 to state 2 is 0.2, but this was a 0 here, so we get multiplied with 0 again, which is 0.6. And the same can be done for the state 3, which results in 0.4. Now we do the same thing again, but we're looking at just this column. For state 1, we get 0 multiplied with 0. We get from state 2 to state 1, it's actually a 1. Plus from state 3 to state 1 is 0.4 multiplied with 0.8. So this value will actually be 0.92. In the same way we calculated for this is 0.08. And for the last one, for state 3, it is 0. We cannot get back to state 3. And this is the third method, which is easier to calculate, better to calculate than the whole matrix multiplication. And there are multiple conditions that you can actually add in these tables. For example, if we said you cannot be in state 3 at t is 1 here, then we can just change this to a 0. We just cannot be there at t is 1. Instead of summing everything, there's also a variation. So we can actually call this method 3.1. And we're now looking at method 3.2, we could call it, because we want to also know what the most probable sequence is. And if we look at the most probable sequence up here, we could actually see, well, this is the endpoint. Then you go to a column before that, you look at the largest value, which was this, and then you go to the largest value again, which was our starting value, and we know our transition to be S1, S2, S1. This is our most probable sequence. However, what they said was, well, we already know that the highest values of probabilities are within our most probable sequence. So instead of adding every value, what we can also do is we are going to take the maximum of the value. So beforehand, we had A of t of a state S is the sum of all states I of, there was t plus 1 for the next one, was AT of a state I multiplied with the transition going from I to S. Is that correct? Yes. So right now they're saying, well, let's not call this A, let's call this B, or in the syllabus they call this alpha, and they call this beta. What they're doing is, well, if you want to know the next one, it's actually not the sum, it is the maximum value of all states. So we're looking at states from 1 between all states n of B T of state j. In this case, we're looking at all j values between 1 and n being the maximum number of states, multiplied with the transition of j to s. The only difference is instead of summing all these values, so here we summed all these values. For example, here we had 1 times 0, 0 times 1, and 0 times 0.8. Instead of summing, we now take the maximum. And this will result in a little bit different table. If we construct the table quickly, we get S1, it's in a different color. We get S1, S2, S3. We get T is 0, T is 1, and T is 2. If we look at the maximum values, we start with the 1, 0, 0 again. Then the second column is still the same, of 0, 0.6, and 0.4. And we can take the maximum value that will still result in the most probable sequence, and that is because the most probable sequence will have the highest probability. So if we just look at the highest probability instead of summing them, we also can get the best, the most probable sequence. And in this case, we see that from 0.6, we go to the largest value again, it's 0.6. We go to the next largest value, which is 1. So we also get our sequence of S2, S1, S2, and S1. So these are 3 or 4 methods to calculate the most probable sequence or the probability that we end up in state 1 after 2 jumps starting from state 0. We can do a lot more with Markov chains, which will be discussed in future videos.